video about pressure. So we're going to talk about a few things that happens when dealing with pressure. First of all, before we begin, let's remember the definition of pressure. It's a force exerted over an area. Okay, and we'll talk a little bit more about that and see pictures on how that gets explained. So some things to know are the units of pressure. ATM stands for atmosphere, kPa kilopascals, mmHg millimeters in mercury. Hg is the symbol for mercury on the periodic table, and torr, which is abbreviated and in full length is actually TORR. What's also important to know are the conversions, right? One ATM has 760 mmHg, one ATM also has 101.3 kPa, and one ATM has 760 torr. All just different ways to express pressure and the relationships between them. Okay, so we're going to be talking about a barometer. And what a barometer is, it's just a device that helps measure atmospheric pressure. And if you remember, there are many gases in our atmosphere. Nitrogen, oxygen, carbon dioxide, argon. It's a mixture of gases. And those gases in our atmosphere that are all around us actually cause a pressure. And we call that the atmosphere's pressure or atmospheric pressure. So how do we measure this atmosphere's gas, this pressure? You know, we don't feel it. We're so used to it on our body, but this gas that's invisible around us actually does do something. Well, we use something called a barometer. And here's a sketch of what a barometer looks like. What appears to be in this picture is kind of like an upside down, well, similar to like a test tube with an open mouth here, sitting in a tray full of mercury. What happens is the gas in the atmosphere, indicated here by these blue dots, right, they exert a pressure on everything. They're hitting the test tube, they're hitting the walls of anything around them, and they're hitting the mercury that's sitting in this plate right here. So they're pushing down on the mercury. This plate on the top is open. As the atoms of molecules push down on the surface of the mercury, that causes the liquid to feel that pressure, and it has nowhere else to go other than to start creeping up the opening of this tube. So the mercury starts to rise inside this tube. More pressure from the atmosphere, the more it rises. This tube right here has a scale on it, and it's in milliliters. So as the pressure increases, more starts to fill up. And then we can actually take a reading. And so therefore, the atmosphere's pressure can be read in this is supposed to be millimeters. Millimeters of mercury. So it measures how high up in millimeters the mercury rises. Hence, one of the units that we saw for pressure, millimeters of mercury. That's where we get it from. So again, this is called a barometer. Okay, let's take a look at some more examples of pressure and some other things that you should know. Here is a balloon. And I blew up some gas inside this balloon, right, from my mouth. So there's a lot of carbon dioxide inside here, okay? And this balloon will say it's a hot, sunny day, okay, right? It's kind of nice and hot in this room I'm in. So if you notice here, the gas molecules are moving around really nice and fast, and they filled up this balloon, okay? What happens when we take this balloon out into colder temperatures is it looks like this. That same balloon, now in colder temperatures, has pretty much shriveled up into a very small size. Okay? Now, have any of the gas molecules left the balloon? No, because if you notice, that balloon is sealed off. So I didn't lose any gas. Then what happened? Well, we know that when gas gets cold, it doesn't move as fast. So that's something important to write down. So let's go ahead and write that. When gas is cold, there's less, and the important word to use here is collisions. the molecules inside are not colliding as fast with each other and the sides of the container. Okay, so let's take a look at these two examples then that we saw here. So here is my balloon drawn. Yes, that's my drawing of the balloon. And here's some gas molecules that are inside the balloon. Here are the gas molecules. For our sake of our picture, we'll just use 3, though there are a lot of gas molecules. And these gas molecules are moving around, but as soon as it turns cold, they actually slow down. They lose kinetic energy. And therefore, there are less collisions with each other and the sides of the container. Okay, now, these collisions with the side of the container, that's what pressure is. The force exerted by the gas on each other and the sides of this container, which is a balloon. So now there's a lot less force because these molecules have slowed down. So what happens? The balloon shrinks because it's not feeling as much. Now, the balloon shrinks because these molecules have less collisions. What about the reverse? All right. Let's bring back our hot balloon again and talk about our hot balloon. So here we are with a hot balloon, and let's bring back a drawing now and our gas molecules. Okay, and what's happening in here? Well, when the gas is hot, it moves around really fast. What could you say about these collisions with the sides of the container and each other? There are a lot. So in a hot balloon, gas collides with the walls of the container, which is the balloon, a lot more often, creating a lot of pressure. Okay? Now, how come this pressure doesn't build up to the point where the balloon pops? Well, that's because of a certain goal in nature, which is this. Nature always tries to keep pressure constant. Constant means the same everywhere. So what does this mean in terms of our balloon? Okay, here's what this means. While these gas molecules moving around fast are exerting a pressure on the balloon, right? Exerting a pressure on the balloon, there's something else pushing on the balloon from the outside. And hopefully you guessed it. That's the atmospheric pressure. All the gas outside the balloon is also pushing on it. So the ones inside are pushing in, and the gas molecules outside are pushing on the balloon. So the balloon doesn't pop because it feels both an outside atmospheric pressure and an inside gas pressure. What happens is the whole goal, right, of nature is that nature wants to make sure that this pressure, wherever it is, inside or out, stays constant, right? So nature always wants this atmospheric pressure to equal whatever pressure is inside something, okay? And a lot of times we like to draw it like this, that the atmosphere's arrow showing pressure is equal in length to the pressure, equal in length to the pressure inside, equal, okay? All right, now let's go back and look again at our shriveled up balloon. So now it gets really cold and we said this happens, right? Let's bring back our old balloon. This happens. Is there still pressure? Of course there is. There's still pressure, but is it as much? No, it's not as much pressure, right? So what happens is initially these molecules slow down and the atmosphere still has a lot of pressure it's exerting, okay? Still has the same amount of pressure, but as soon as those gas molecules slow down, the atmosphere pressure kind of wins and it pushes on the balloon. So in a sense, the arrows are not the same. So let's show what that means, okay? In this instance, the atmosphere its pressure is a lot more than the inside of the balloon. Notice the smaller arrow inside the balloon. So the atmosphere is what pushes that balloon in because it's still applying its pressure. And also the fact that the molecules have slowed down have caused this to happen as well. Okay? So the goal of nature is to always to keep things the same. How is that happening? Well, as the balloon decreases in volume, right, seen here, now the gas molecules can reach the sides a lot quicker because the volume is smaller, right? They can reach that side a lot quicker. So they're in turn applying, once again, more pressure, right? So they're kind of trying to equal out that pressure between the atmosphere and inside the balloon. If the balloon is this big, gas molecules might not be able to hit it as much when it's cold. If it's cold and the balloon shrinks, now gas molecules can re-hit them. They're not hitting very fast, but at least they're trying to equal out the pressure. So that is important to note. Okay, so let's make sure that we've written down those things about that the atmosphere pressure keeps pushing on the balloon, and the pressure inside is trying to equal the pressure outside. Okay, the only way to do that is by shrinking the volume of the balloon so the gas can hit the walls again and apply pressure. Okay, those are some concepts that you should think about and use in other scenarios, not just balloons, but they can be used in many other examples.